Now, let's say if I have this series right over here from n is equal to 1 to infinity of 2 to the n. Now, as soon as you look at this series, you might be like, oh, this is very easy. This diverges. And just to recall, when a series converges, that means it sort of settles on a value if you add all of those terms up together, right? And if a series diverges, that means you're not really settling on a value. So it could be approaching infinity, negative infinity, or even oscillating between two values. But the point is that you're not really settling on a value. If you take a look at this series right over here, if n is equal to 1, that's going to be equal to 2. If n is equal to 2, that's going to be equal to 4, 8, 16, 32. So our terms get bigger and bigger and bigger. So if I add all of these terms up together, it's pretty much gonna approach infinity, right? It's not really gonna approach a specific value because it's just gonna keep getting bigger. Now, let's use that logic and connect that to integration. So on this function right over here, this function is f of x is equal to 2 to the x. So it's pretty much it's sort of like the exact same thing as this, right? It's sort of like the series is sort of represented as a function. All right. Now, if I were to express this sort of series as a function, well, take a look. As my values approach infinity, so as my sort of y value approaches infinity, if I try to take the area underneath this curve, it's also going to approach infinity. All right. So if my function is sort of increasing at all times, that means that my area underneath the curve is going to approach infinity, right? It's going to approach infinity. And that's sort of like the basis of something known as the integral test. The integral test basically states that if you have some sort of infinite sum, let's say this is from, let's just call this n. Let's say it starts from n, capital N. And let's say that this approaches, I'm adding all of this up to infinity, right, of some specific series, right? If I can express this series right over here as a sort of function, so let's say if I can express this as a sort of function, and I integrate this function from the same bounds, so from n to infinity, well then, if the integral right over here diverges, then so does my series. And if my integral converges, then my series also converges. And this sort of makes sense because if my function is constantly increasing, then if I try to get the area underneath the curve, well, I'm not really going to be able to, right? There's always just going to be more and more area for me to cover. So that's going to approach infinity, right? And likewise, if I had a function that looks maybe something like this, where, you see that the area underneath my curve is actually approaching a specific value, then that means that this series right over here is also going to approach a specific value, right? And when you're converting from sort of a series into a sort of function, you actually have to make sure that the function is positive, decreasing, and continuous. You want to make sure that this is positive because if your function, for example, looks something like, if your series looks something like this, where it sort of alternates between like positive and negative values, well, then you would probably want to use like an alternating series test or something like that, right? So yeah, you just have to make sure that your function is positive, so it doesn't really alternate. It's like something like this. You have to make sure that your function is decreasing, right? Because if you have a function that's increasing as well, it's obviously going to be diverging because, well, the function is just getting bigger and bigger. And usually you could just see that right from the start. Like just looking at this series right over here for 2 to the n, you could just already see that your terms are going to get bigger and bigger. So this is going to diverge. You'll need to use the integral test for this. And also, your function has to be continuous. Let's actually do a practice problem to apply this. All right. So we have this series right over here, 1 divided by n ln of n. And let's use the integral test to sort of solve this. Also, there should be an infinity up there. Sorry, guys. But yeah, here we go. First of all, I want to convert this into a function. So let's just convert this into f of x being equal to 1 over, and then replace all the n's with x's. So x ln of x. All right. Now, we want this to be from 2 to infinity, right? So you kind of have to ask ourselves, when our x value is from 2 to infinity, is our function positive, decreasing, and continuous? If it meets all three of these criteria, then we can use the integral test. All right. Now, is our function positive from 2 to infinity? Well, yes. Whatever x values you put in from 2 to infinity, if you plug in a positive value for x, that's just going to be positive. If you plug in a positive value for ln of x, that's also going to be positive. Positive divided by positive is always positive. So, boom, it is positive. Is our function decreasing? Well, yes, because as we plug in bigger and bigger x values, well, our denominator increases. If our denominator increases, the whole value is going to decrease. So our function is decreasing, and it's also continuous. You can plug in any value here, and it will work. Therefore, we can use the integral test. So this is going to be equal to, we're going to create the integral now. So this is going to be equal to, not equal to, but this is going to be the integral from, in this case, from n is equal to 2 to infinity. So we keep kind of the same things as our series. And this is going to be for our function 1 divided by x ln of x dx. All right. I'm just going to get rid of that real quick. All right, let's see how we integrate this. I see ln x. I know the derivative of ln x is 1 over x. So it looks like a little bit of a u substitution scenario. I'm going to get my u value. I'm going to get my u value be equal to ln of x. If I differentiate this, du is going to be equal to 1 over x dx, right? And if I want to substitute dx right over here, if I multiply both sides by x, I'm going to get x du is going to be equal to dx. All right, let's do the substitution now. I know u is equal to ln of x, so let me substitute u there. Infinity to 2 of, and then it's going to be, there's going to be a u instead of ln x here, and then you're going to keep this x. And I know du is going to be 1 over, I know that x du is going to be equal to dx. So this dx right over here, I'm just going to replace it with x du, okay? The x's cancel out, and I'm going to get the integral from infinity to 2 for 1 over u du. I prefer not to change my bounds of integration. So what I'm going to do is, once I get my desired value, then I'm going to resubstitute back in ln x for u, and then after that I plug in my bounds. So here's what I mean. So 1 over u, of course, integrate that. That's going to be ln of absolute value of u, right? And we have to evaluate this from infinity to 2. So it's going to be from infinity to 2. Now, before I plug in my bounds, I have to make sure that I resubstitute ln of x back into here. So I'm going to get ln of the absolute value of ln of x. Okay, and this is still going to try to evaluate this from infinity to 2. Now, what happens if I plug in sort of infinity for ln of x? What happens if I try to plug in a very big number into x? Well, this whole thing is just going to be really big, right? If I plug in a very big value for there, then we're just going to get a very big value. Therefore, all of this evaluated at infinity is essentially just infinity, and this is going to be subtracted by ln of the absolute value of ln of 2, right? Because then we plug in 2 in here. So therefore, infinity minus that, well, infinity is just going to outgrow that. So, boom, we get that. When we did the integral test, we found out that our indefinite integral is infinity, right? It's going to approach infinity. And therefore, the series right over here is going to diverge. This is going to diverge. Let's say that we have this series right now. What should we do? Well, first let's just convert this into a function. So this is going to be f of x being equal to 1 over x squared. All right. Now, what we have to do now is we have to make sure that our function is positive from, in this case, n is equal to 1 to infinity. You have to make sure that's decreasing and continuous. Our function is, of course, positive because from 1 to infinity, because if you plug in sort of any value right over here, well, it's always going to be positive. Actually, even any negative value would work, because if you plug in a negative value, negative squared is going to be positive. So either way, this function is always going to be positive. It's always going to be decreasing as well because we have x squared in the denominator. So as our x value increases, our denominator gets bigger, which makes the whole value smaller. And it's continuous. So yeah, let's get started. So we can rewrite this as the integral from, in this case, 1 to infinity of our thing. So 1 over x squared dx. And then now we can just solve this integral. This is the same thing as x to the negative second power, right? So I'm going to write this as integral of 1 to infinity of x to the negative second power. And then I could just apply the reverse power rule. I could say this is just going to be x to the, add 1 to it, and then divide by that. So this is going to be negative 1 over x. And then this is going to be evaluated from infinity to 1. Imagine if we plugged in infinity somehow into our denominator. Well, if our denominator is a very, very big value, our whole value is going to be very, very small, right? So therefore, it's actually going to be 0. If we plug in 1 here, this is going to be subtracted by this evaluated at 1. So if I plug in 1 into here now, I get negative 1 divided by 1, which is just negative 1. 2 negatives negative positive. 0 plus 1 is equal to 1. Because our improper integral converges, that means that our series, the series right over here, converges. It converges. All right. Recall that this is actually a famous infinite sum right over here. This is actually going to converge to this pi squared divided by 6. So this integral doesn't give the exact value. All right. So just remember that the integral just tells you if it converges or diverges, but it doesn't give the actual thing that it converges to. Final one, convert this into a function, 1 over x ln of x squared. That's our f of x. Is this positive? Yes. Right? If we plug in any number from 2 to infinity, well, our x values are always going to be positive, right? Whatever x value we plug in is positive. Ln of x squared is always going to be positive, right? So all of this is positive. It's always decreasing because you see a lot of it on the denominator. All of the x's are on the denominator. Denominator is constantly increasing. Actual value is decreasing, and it's continuous. So let's get straight into it. Integral of, and then this is going to be from the same bounds. Oh my god! Boom! There we go. Same bounds as we had before, 2 to infinity. This is going to be of 1 over x ln x squared dx. And whoa, barely have any space left. Let's solve this. Once again, we're going to use u sub, so u is going to be equal to ln of x. Du is going to be equal to 1 over x dx. So that means dux is equal to dx. Okay, now let's get started. So u is equal to ln x, so I'm going to have integral from infinity to 2 to infinity of this. I substitute in u in for ln of x, so I get u squared. Instead of ln of x squared, I get u squared. And then instead of a dx, right, I get dux. The x's cancel out, so I'm just going to be left with integral from 2 to infinity of, in this case, 1 over u squared du. And now we can just use our reverse power rule. So this is the same thing as 1 over u squared is the same thing as u to the negative second power. So then just do the reverse power rule. And actually for this problem, it might actually be easier to change the bounds. Like you don't have to change the bounds. Usually I do not like to change the bounds. But it looks like for this problem, let's just change the bounds for the fun of it to, I don't know, I guess to practice. So look, this is, originally we had x is going from 2 to infinity. All right. And now we have u, and we want to know the bounds of u. We want to know where it goes to. All right. The top and the bottom. Now, as our x value approaches 2, u is going to approach ln of 2, right? Because u is equal to ln of x. So if x approaches 2, u is going to approach ln of 2, right? And as x approaches infinity, well, u is also going to approach infinity, right? Because u is equal to ln of x. So as our x value approaches infinity, u is also going to approach infinity because ln of a very, very, very big number is also going to be just a very, very, very big number. It's just going to keep getting bigger. So, so instead of 2 right over here, I'm just going to put ln of 2. And then for my top bound right over here, it's still going to be infinity. Okay. Now we can do a little bit of u to the, this is u to the negative first power, negative, it's going to be negative 1 over u, and this is going to be from ln of 2 to infinity. If I plug in infinity here, once again, you get a very big denominator, you get out a very small value, so this is going to be essentially approaching 0, and this is going to be minus, well, if we plug in ln of 2 here, well, I'm going to get negative 1 over ln of 2, so I'm going to get negative 1 over ln of 2. So negatives cancel out, negative negative makes a positive, so I just get 1 over ln of 2. Because our integral converges to a finite number, well, our series is also going to converge. So there we go.